In 2023, the wreck of the Titanic claimed 5 more lives. As OceanGate's Titan descended toward the wreck, nearly 13,000 feet beneath the surface of the North Atlantic, all communication with its support vessel, Polar Prince, was lost. For 4 days, its fate remained unknown as a search and rescue operation searched the North Atlantic. Although those aboard Polar Prince heard what was later confirmed to be the sound of the implosion,
500 meters, 30. What was that thing?
no one recognized its significance at the time. The U.S. Coast Guard and Canadian authorities continued searching for 4 days, hoping Titan was disabled on the seafloor. It wasn't until June 22, 2023 that the search ended, when Titan's wreckage was located 1,600 feet from the bow of the Titanic, confirming what many had already feared. The submersible had suffered a catastrophic implosion, killing all 5 on board. Among them was OceanGate founder and CEO Stockton Rush, the man who had designed the experimental submersible. 3 years after the Titan implosion, investigators have finally pieced together what doomed OceanGate's submersible. 3 separate investigations have now reached the same conclusion, revealing a disaster that began long before Titan's final descent to the Titanic in 2023. The carbon fiber hull, often blamed as the sole cause, was only part of the story. In reality, the chain of events that ended in catastrophe was set in motion a full year earlier, during a dive from which everyone walked away. One of the investigation's most significant findings challenged one of the earliest assumptions about the disaster. The Canadian investigation concluded that, under ideal manufacturing conditions, Titan's pressure hull was predicted to have a substantially longer fatigue life than it ultimately achieved. Before its final dive, the submersible had successfully reached the Titanic on 13 expeditions. Their analysis indicated that a defect-free pressure hull of the same design could have remained structurally sound for hundreds of additional pressure cycles. If the design itself was capable of surviving, what caused Titan to fail? Part of the answer lies in the geometry of the pressure hull. A cylinder subjected to extreme external pressure does not distribute stresses as efficiently as a sphere. The greatest deformation occurs midway between the supporting end caps, where bending stresses are highest. A spherical pressure hull, by contrast, distributes compressive loads almost uniformly in every direction, making it inherently more resistant to collapse. For that reason, virtually every successful crewed deep-sea submersible, from the bathyscaphe Trieste, which reached the Challenger Deep in 1960, to James Cameron's deep-sea Challenger, as well as Titanic diving submersibles such as Nautil, Alvin, and Mir, has relied on a spherical pressure hull. OceanGate, nevertheless, chose a cylindrical design. The reason was largely practical. A sphere offers exceptional structural efficiency, but makes poor use of interior volume. A cylindrical cabin provides sufficient space for 5 occupants to remain together inside a single pressurized compartment, something that would have been difficult to achieve with a sphere of comparable size. That additional interior volume made the design far more attractive for commercial tourism, allowing OceanGate to carry more passengers per dive while providing a shared cabin experience. The trade-off was that the pressure hull became significantly more demanding to design, manufacture, and inspect. Now, a cylindrical pressure hull is not inherently unsafe. Naval submarines have relied on cylindrical pressure vessels for decades. In fact, the Soviet K-278 Komsomolets still holds the record for the deepest dive by an operational combat submarine, reaching approximately 3,350 feet. That achievement, however, remains the exception rather than the norm. Most modern military submarines operate at depths of only a few hundred meters, with estimated maximum operating depths of around 1,500 to 2,000 feet. Even the record depth achieved by the K-278 was only about 1/4 of the depth required to reach the Titanic. OceanGate itself had already demonstrated that a cylindrical pressure hull could operate safely, but only at far shallower depths. Its first crewed submersible, Cyclops 1, featured a cylindrical steel pressure hull with a large acrylic viewing dome. Unlike Titan, however, Cyclops 1 was certified to depths of approximately 1,650 feet, less than 1/7 of Titan's intended operating depth. Why, then, didn't OceanGate simply build Titan from steel? The answer lies in the engineering trade-offs. A steel pressure hull capable of surviving nearly 13,000 feet beneath the surface would have required substantially thicker walls, dramatically increasing the vehicle's weight while reducing its usable interior space. Carbon fiber composites offered the possibility of a lighter, roomier pressure hull capable of carrying 5 occupants to Titanic depth, a key advantage for OceanGate's commercial business model.
What have you done to make sure Titan can survive a trip to Titanic?
It's been a long process to ensure that Titan can go to the Titanic repeatedly and safely. We've refined the process so that we have extremely uniform 5-inch thick carbon fiber.
Titan combined a demanding geometry with a carbon fiber composite pressure hull and titanium end caps, one of which was manufactured from Grade 3 titanium rather than the stronger Grade 5 alloy originally proposed during the design process. Individually, none of these design decisions guaranteed failure. Together, however, they left the submersible with significantly less tolerance for manufacturing defects, progressive damage, and unforeseen loads than conventional deep-sea submersibles.
There are certifying agencies, the Pressure Vessels for Human Occupation Committee, the SubSafe program in the Navy. These programs are over the top in their rules and regulations, but they had nothing with carbon fiber. So we had to go out and work on that. And one of the things I learned is, when you're outside the box, it's really hard to tell how far outside the box you really are. And we were pretty far out there.
The investigation reports indicate that carbon fiber itself was not the primary problem. Properly manufactured, it is one of the strongest structural materials ever developed, offering an exceptional strength-to-weight ratio that exceeds that of steel. The challenge lies in how composite materials fail. A carbon fiber pressure hull is not made of carbon fibers alone. Thousands of microscopic carbon strands are bonded together by an epoxy resin, which transfers loads between the fibers, keeps them aligned, and gives the laminate its overall shape. While the carbon fibers provide most of the strength, the epoxy matrix is far more susceptible to microscopic cracking under repeated loading. As those cracks grow, the bond between individual layers can begin to separate, a process known as delamination, allowing damage to accumulate deep within the structure long before any signs appear on the surface.
Oh dear. What am I looking at?
These are the results of some of our pressure tests. This is a 3rd scale model of the Titan hull. You have the cylindrical section, and you have the domes that we originally thought we could make out of carbon fiber.
The geometry of Titan's pressure hull further complicated this behavior. Unlike a sphere, a cylindrical pressure hull does not distribute compressive loads uniformly. Fibers wrapped around the circumference of the hull carried the external pressure efficiently, but the longitudinal fibers terminated at the titanium end caps, where they experienced complex stress concentrations. Those non-uniform load paths made the composite laminate more sensitive to manufacturing defects and progressive damage than an equivalent spherical pressure hull, in which compressive loads are distributed much more evenly. Those stresses were repeated during every dive. As Titan descended, the pressure hull was subjected to immense external compression. During ascent, those loads were released. Unlike metals such as steel or titanium, carbon fiber composites can accumulate hidden internal damage that remains virtually impossible to detect through visual inspection alone. Microscopic cracks can develop within the epoxy matrix. As that damage accumulates, the pressure hull loses stiffness, forcing the remaining intact fibers to carry progressively larger loads. Once enough of the laminate has been compromised, catastrophic failure can occur with little or no visible warning.
So this would have been a sub you don't want to be in.
This is true.
But I assume also a valuable lesson, this test.
Yes, one element we were looking at is, could we predict the failure of carbon fiber? So a carbon fiber sub may work great for 1 dive or 10 dives or 100, but will it get soft like the deck of your fiberglass boat after somebody's been stepping on it too much?
Right.
And how do you know that before somebody gets hurt?
Right.
And there's been a bunch of work on acoustic emissions. So basically we're listening to the sound of the carbon. They start popping and crackling. These micro-buckling pieces, little air bubbles go and fibers snap. And we found that you can tell quite clearly way before the carbon fails that it's going to fail. And that would allow
You can hear it.
Yes. So if you get to 2,000 meters and it's making more noise than the last time you went to 2,000 meters, you can stop and go to the surface and say, we got a problem.
Okay, so in the end, have you cracked the code?
I think we've cracked the code.
The Canadian investigation compared an ideal pressure hull with the one Titan actually received. Imagine bending a paper clip back and forth. Every bend weakens it slightly until it eventually snaps. Engineers call that fatigue. Every dive to the Titanic was one more bend in Titan's pressure hull. According to the investigation, a perfectly manufactured hull would have barely noticed those dives. After 24 pressure cycles, it would have used only a tiny fraction of its expected service life, leaving hundreds of similar dives still ahead of it. Titan's actual hull told a very different story. Based on the weakest material samples recovered from the wreck, investigators estimated that those same 24 dives may have consumed more than 80% of its predicted fatigue life. Instead of barely aging, the hull had already used up most of its expected lifespan. The investigation also uncovered another problem. Engineers don't build structures to survive exactly the expected load. They build in extra strength as a safety margin. OceanGate's design called for a safety factor of 1.25, meaning the pressure hull should have been able to withstand about 25% more load than required. Testing showed the finished hull received only about 1.11. That reduced margin did not guarantee failure, but it left the structure with far less tolerance for manufacturing defects, damage accumulation, or unexpected loads. The investigation also found that many of Titan's problems originated during manufacturing. Instead of being fabricated as a single 5-inch thick laminate, the pressure hull was built in 5 separate 1-inch sections, each cured before the next was added. This meant the innermost layer, the one subjected to the greatest stresses during every dive, underwent 5 separate curing cycles, repeatedly exposing it to heat that may have degraded its long-term mechanical properties. In addition, during fabrication, sections of the carbon fiber developed wrinkles where the fibers buckled instead of remaining straight and aligned. Because composite materials derive much of their strength from continuous, properly oriented fibers, these wrinkles significantly reduced the laminate's structural efficiency. OceanGate attempted to correct these defects by manually grinding the wrinkles away. However, the investigation found that this repair often displaced the distortion into the adjacent layer rather than eliminating it entirely. In some samples, investigators identified as many as 12 ground repair locations, suggesting that correcting one defect frequently created another deeper within the laminate. Investigators also found numerous microscopic air pockets, known as voids, trapped within the epoxy resin. On average, these voids occupied about 2.7% of the laminate's volume, reducing the composite's overall strength. They also made the finished pressure hull too thick to fit properly inside the titanium interface rings. To compensate, OceanGate machined material from the outer surface of the hull, removing some of the very carbon fibers intended to withstand the immense external pressure. Perhaps most significantly, the completed pressure hull no longer matched the original design. An early feasibility study by Boeing proposed a wall thickness of approximately 7 inches. Titan's production hull measured only 5 inches. The final design also omitted the plus 45-degree carbon fiber plies originally proposed to resist shear stresses within the laminate. When investigators asked why these changes had been made, no documented engineering justification could be produced, and Boeing had not been consulted after its initial feasibility assessment. When investigators tested samples from Titan's pressure hull, they discovered that its strength varied dramatically from one section to another. The results ranged from 6.92 ksi to 12.05 ksi, a difference of nearly 2 to 1. In other words, some areas of the hull were almost twice as strong as others. In a structure designed to withstand thousands of pounds of pressure per square inch, that kind of inconsistency meant the hull could only be as strong as its weakest section. The significance of those findings became clear when investigators examined an earlier dive.
All right, good morning, everyone. Headed back to the Titanic. Right now, we did vessel checks this morning. A couple very minor anomalies, which is great.
On July 15, 2022, almost a year before the implosion, those aboard Titan heard a loud bang while ascending from Dive 80. OceanGate documented the event, but concluded that the pressure hull was simply settling into place, and operations continued.
When we got to the surface, Scott was piloting. He heard a really loud bang, not a soothing sound. No. But on the surface, and as Tim and PH will attest, almost every deep diving sub makes a noise at some point. You have just similar shapes and metals that are expanding due to thermal interaction, due to pressure changes, and it's quite common to have a noise.
The recovered wreckage told a different story. Investigators found extensive delamination between the first and second laminate sections, and again between the third and fourth, the same locations where manufacturing defects had been previously identified. Investigators also found wear marks and debris trapped between the separated layers, indicating that the laminate surfaces had been rubbing against one another before the final dive. These findings suggest that significant internal damage had already developed well before Titan's last descent. Despite the acoustic event on Dive 80, the submersible returned to Titanic depth on Dives 81 and 82. Internal monitoring data from Dive 80 was reviewed by OceanGate management. According to testimony presented during the investigation, Stockton Rush's response was, "Let's dive again and see what happens." As a safety measure, OceanGate equipped Titan with an acoustic and strain gauge monitoring system designed to detect structural damage before it became critical. Strain gauges measured how the pressure hull deformed during each dive, while acoustic sensors listened for the sound of fibers breaking inside the composite laminate. In theory, the system could provide an early warning of failure. The problem was not the data, it was how the data was analyzed. OceanGate focused on strain against time during each dive. Investigators instead plotted the same data against depth, where external pressure steadily increases. The difference was striking. Before Dive 80, Titan's strain closely followed a straight line relationship with depth, indicating the pressure hull was behaving as expected. After Dive 80, that relationship changed. At shallow depths, roughly the upper 500 meters, the strain response became non-linear, while at greater depths, it remained largely unchanged.
This picture here is of the placements of the acoustic emission sensors on the Titan. The purple you see here, this is the acoustic emissions, basically the energy or acoustic data that was heard on Dive 80. This purple line goes all the way to the top, which means it was a loud bang. There is this huge amplitude. Stockton Rush touted this system as it will let me know something is happening before something bad happens, right? Their system did that. Their system said there has been a fundamental change in the material of your carbon fiber, and it was no longer structurally sound like it had been prior to Dive 80. Delamination at Dive 80 was the beginning of the end. And everyone that stepped on board the Titan after Dive 80 was risking their life.
Near the surface, where external pressure was relatively low, the separated laminate layers were free to move independently. As Titan descended, the immense hydrostatic pressure forced those layers back together, temporarily restoring much of the hull's apparent stiffness. In effect, the damage became partially concealed at operating depth. When investigators compared the strain measurements with the acoustic monitoring data and the loud bang reported during Dive 80, they concluded that all three pointed to the same structural event. The pressure hull had already sustained significant internal damage nearly a year before the final implosion. Even after Dive 80, Titan continued operating under conditions that investigators believed may have worsened the existing damage. Composite pressure vessels are typically stored in climate-controlled environments to protect them from moisture, sunlight, and temperature extremes. Instead, Titan spent the winter of 2022 through 2023 uncovered outdoors in St. John's, Newfoundland. Investigators noted that if water entered existing delaminations, repeated freeze-thaw cycles could have forced the separated layers farther apart. The method of transportation also changed. Rather than being carried aboard its support vessel, Titan was towed approximately 900 miles across the North Atlantic behind Polar Prince. Already containing internal delamination, the pressure hull was subjected to continuous wave impacts, vibration, and bending loads throughout the voyage. During one launch, the submersible also repeatedly struck its launch platform for nearly 45 minutes. The National Transportation Safety Board concluded that Titan's pressure hull sustained additional damage after Dive 82, but could not determine exactly how it occurred. Whether caused by towing, environmental exposure, operational impacts, or a combination of factors, the result was the same. An already damaged pressure hull continued to deteriorate before its final dive. OceanGate's safety philosophy relied heavily on real-time structural monitoring. Microphones bonded to the pressure hull were designed to detect the sound of carbon fibers breaking, while strain gauges measured how the hull deformed during every dive. In theory, the system would warn the crew before catastrophic failure occurred. Investigators found several problems with that approach. 3 of the 8 acoustic sensors were inoperative during the 2022 and 2023 seasons. The monitoring system erased its history after every dive, making long-term damage difficult to track. Acoustic events recorded on the surface were frequently dismissed as routine handling or docking noise. More importantly, Boeing engineers testified that Titan's actual failure mode might not have produced the type of acoustic signature the system was designed to detect. In other words, the system was listening for one kind of failure, while the pressure hull may have been failing in another. The warning signs were already there. Throughout the 2021 season, Titan recorded no significant acoustic events. After Dive 80, the pressure hull was no longer behaving as it had before. Investigators concluded that OceanGate had become increasingly accustomed to these warnings. In engineering, alarm systems that generate frequent false or unexplained alerts eventually become background noise. Instead of triggering a comprehensive investigation, Titan's growing number of warnings became part of normal operations. The final irony was striking. Titan's onboard monitoring system never identified the failure that destroyed the submersible. Yet a U.S. Navy hydrophone array nearly 1,450 kilometers, about 900 miles away, detected the acoustic signature of the implosion within minutes of the loss of communications. Titan's loss did not mark the end of crewed exploration of the Titanic. Later this year, Triton Submarines plans to return to the wreck with its new Triton 4000 Abyssal Explorer. Designed to carry 2 occupants to depths of up to 13,000 feet, the submersible takes a fundamentally different engineering approach from every other submersible. Rather than relying on steel, titanium, or carbon fiber, the Abyssal Explorer features a fully transparent spherical pressure hull made entirely of acrylic. Traditional deep-diving submersibles typically house their crews inside steel or titanium spheres, viewing the outside world through relatively small acrylic windows. Triton's design instead makes the pressure vessel itself transparent, providing an unobstructed panoramic view while retaining the inherent structural advantages of a spherical hull. The submersible measures 15 feet long, 9 feet wide with its gull wings retracted, and 20 feet wide when fully deployed. Its weight is approximately 26,500 pounds and is capable of remaining submerged for more than 12 hours using redundant life support systems. A unique silent glide mode allows the submersible to coast through the water with minimal thruster use, reducing noise and disturbance during scientific observation and filming. The concept is unprecedented for a submersible operating at Titanic depth, and its unconventional design has inevitably drawn comparisons to Titan. The similarity, however, largely ends there. Unlike Titan, the Abyssal Explorer is undergoing independent verification and certification to internationally recognized standards. Triton has already demonstrated its engineering capability with the Limiting Factor, the first commercially certified crewed submersible with a pressure hull tested to withstand up to 46,000 feet. It's been widely marketed as having unlimited depth rating, diving multiple times to Challenger deep. The technology to reach the Titanic safely has existed for decades. The investigations into Titan did not conclude that deep-sea exploration was inherently too dangerous. They concluded that engineering discipline, rigorous testing, independent verification, and conservative design margins remain essential. The central lesson of the Titan investigation extends far beyond a single submersible. The Titan disaster has now changed how composite pressure vessels, structural health monitoring, and privately operated deep-sea submersibles will be evaluated for years to come. If the lessons identified by these investigations are applied, that knowledge may ultimately help prevent another tragedy. If you are interested in the full OceanGate story, check out my video about the rise and fall of OceanGate. Thanks a lot for watching, and I'll see you in the next video.